Okay, so lecture 27, Theta-Angle and Instantons. Today I'll try to use this side of the board because I don't know if you see, because I have to write some stuff. Any questions from the previous lecture? So in the previous lecture, we started talking about topics in gauge theory. In particular, we discussed monopoles and Dirac quantization, theta term in electromagnetism, and today we're going to talk about the role of theta term in quantization and instantons. So what does this mean? Just to put things in the context, we said that the theta term is topological. It does not change classical equations of motion. So it has no consequences classically. What about quantum mechanics? It turns out that it does have effects in quantum mechanics. We're going to discuss that. So that's what I mean by theta term and quantization. The spectrum of the theory depends on the theta term. And then we're going to talk about instantons. So instantons, let me just give you a one-liner definition to have in mind for now. Imagine Euclidean quantum field theory, right? So it's a path integral of this type over h bar. In the saddle point approximation, we approximate this path integral with the on-shell action, right? S of phi classic. We saw that in effective action, there are h bar connections to this, right? Actually, it's one of the h bar. Good. Classically, this is the only thing that we care about, right? Now, phi classical comes from finding solutions to the equations of motion. What if there are several extrema of the action? When there is, so there one setup that we observed a lot is that phi classical equal to 0 was a solution often, right? We're gonna see setups like that, but sometimes, so this is a function of Euclidean space-time. Consider a non-trivial function of Euclidean space-time that solves the Euclidean equations of motion. That's called an instant. Good. A non-trivial solution. Now, often these are non-trivial topological field configurations. We're going to give examples of that, right? So they're very important in many ways, but we're going to discuss that. We're going to discuss instantons today in the context of gauge theories. Good. Before I talk about gauge theory, before I talk about magnetic monopoles and reviewing the stuff from last week, let me remind you how we came up with gauge theories. So this is a reminder of lecture QFT1, the stuff that we went over. We said that in gauge theories, we're dealing with theories that have non-localities, right? What was the manifestation of non-locality? Sorry? Wilson lines, Wilson loops, but more on-off effect, right? You look at the Wilson loop here, right? The value of that did not, so A mu is the field. Sorry. Let me not. The value of that depended on the flux that was going through somewhere inside, right? As we're integrating this, nowhere along the integral we're dealing with this. So if there was just some small region where there was flux lines coming down, right? The value of this will depend on that. if you recall, what we said was that, well, every time you have this, the gauge field, so gauge field came about when we tried to insist on a local description, right? Every time there was something like this, there was some sort A mu could corresponded to a non-trivial gauge transformation, topologically non-trivial gauge transformation, right? Here, so let me clarify that again. The physical thing is magnetic field and E, right? F mu. At every point here along this path, F mu is 0. But the result of this interval depends on this part, right? And that had to do with that. For that, to fix that, we introduced this degree of freedom A mu. A mu had a gauge freedom, right? So at each point, if this this is a we thought of this as an S1. So let's say there's a U1 theory. If there's no flux here, you could trivialize this bundle at every point. You could set A mu at every point. When there's flux here, depending on the number of units of flux, there's topological obstructions. So this at every point locally is a pure gauge transformation, right? But as we go around, topologically it's non-trivial configuration. You cannot set it to 0. You could at every point, at this point you could set it to 0, at this point you could set the A mu to 0, but you can't go around and set 0 everywhere. Somewhere along the circle, you'll have to pay a cost. Now, the value of this integral was actually fixed by the number of flux that was going through this. It's topological, right? Because you can think of A mu. What is A mu? A mu is a map from the gauge group, from space-time, R3, 1, to the gauge group, U1. That's what it means to have at every point in the circle, right? Yeah. So there's the there's the homotopy theory, blah blah blah. But let me not talk about that, right? So hopefully now you recall the issue with there was this fundamental non-locality in gauge theory. It had to do with the fact that the observables were F mu nu, and we had setups where F mu nu around the path was 0 at every point, but we had an observable which was non-zero. It was a Wilson loop, and to make sense of that, we introduced a gauge field, a local degree of freedom gauge field. It had this redundancy, gauge redundancies, but large gauge redundancies, topologically non-trivial gauge transformations are physical. They encode these non-local observables for the time. Good. All right. So keep that in mind. This whole story of this previous lecture and this lecture are going to be about these topological non-trivial gauge configurations. And they're absolutely essential to gauge theories. They're in the core of the idea of using A mu, introducing A mu. All right. So, yeah.
You say large gauge transformation.
Yeah. So, right. I shouldn't say topologically non-trivial. Yeah, I'm using the word large gauge transformation loosely. Yes. Topologically non-trivial gauge transformations. All right, so magnetic monopole. Magnetic monopole is some object that creates radially outwards or inwards, depending on the charge, magnetic field, right? And then there is some sort of a Coulomb law for it. If it exists, it would modify Maxwell equations by introducing magnetic charge density, magnetic current. We said that if they exist, right? This sits here. There is this flux that it creates, exactly like here. There's some flux that it creates. Now you take an electron, you take it around the loop, right? you pick up this phase. And it has to do with the fact that the presence of the fact that there's flux going through this means that you end up with a mu along the path, which is topologically non-trivial. So you cannot set it to 0 at every point. And the fact that you cannot set it to 0 at every point, it has to be multi-valued, right? As you go around the circle, right? There will be some sort of quantization. Well, okay, so let me not jump ahead of myself. All right, so now this integral is going to be equal to the amount of flux that goes through this, right? The amount of flux is related to solid angle G over 4 pi, right? And solid angle over 4 pi because this is radial going up. Now, there are two choices to consider, right? One choice is this flux going through this, and the other one is flux going through the other side of it. They would differ by this 4 pi minus omega, right? Which tells you that the fact that the result of this calculation should not depend on which one we pick tells you that there has to be charge quantization. E times G is 2 pi NH bar. Importantly, this really didn't matter that one of them was electric, the other one was magnetic. In a theory that has both electric and magnetic charges, there are in general particles called dyons. They have electric charge E and magnetic charge G. So dion number 1 is sitting in the middle with E1, G1. You take a dion number 2, you turn it, do a loop around it, that's E2, G2. And the quantization condition is E1, G2 minus G2, E1, G2 minus E2, G1 is 2 pi and H bar. Where is the H bar coming from? Yeah, but like if you wanna know, it's coming from here, right? So it's e to the power of, yeah, actually, as a matter of fact, yeah. I said that already. You could view it as eating it in the coupling, or you could view it as action over H bar. This is coming from an action. So that's the charge quantization. So we said, okay, naively, the fact that B has to be Carol of this gauge vector field, seems to imply that there can't be magnetic charge density. The divergence of B is 0. But that's assuming that the A vector field, vector potential is non-singular. We gave an example of a setup where we wrote down precisely this gauge configuration, a vector field, A n of I, right? Which on the upper it produces a right B, right? It produces a right B, but it has this line of singularity here. Then we did a gauge transformation, right? It produces the correct B everywhere, but it has a singularity here, right? So now think of this. So now these two are related by, as we go around this, by a shift in G. So this is a non-trivial gauge transformation, right? As you go around, so it's topologically non-trivial as you go around this pi circle. Good. It's a higher dimensional analog of this circle that you're doing with U1 that I gave as an example. All right. In general, let me say a few words about, this is again, reminder about gauge theory. So we said that in the geometric picture of gauge theory, we think of the gauge field. What we have is a fiber bond, let's say principal bundle. At every point in space-time, this is manifold space-time, there is a gauge group. And a gauge transformation is a particular transformation around this gauge group, right? It's a particular member of this Lie group, right? Now, A mu A was, or A mu, the non-abelian one you have to expand, it's Lie algebra valued, is a connection, right? We said that we needed connection so that we can make sense of the derivatives for charged matter to put in the action, so that we could compare the value of the gauge field. So the value of the charged matter at this point and another point. So this gauge transformation is Lie group valued, right? And then you could think of it as exponentiation of a Lie algebra value thing, omega A, and Ta are the Lie algebra things, generators. So I'm pretending Ta, I was using that notation for SUN, but you know what it is. So when under gauge transformation, the connection transforms this way. If you're at a point, you could set your gauge field to 0 using, you could try to use gauge transformation to set it equal to 0 at the point, right? And you do this at all sorts of different points. If at every point, A mu of A could be written as del mu of omega of A of X, this is a pure gauge transformation. But it could be non-trivial. If omega A is topologically non-trivial, you cannot set it to 0. So here's the first connection to instantons. When you have A mu of A equal to 0 as a vacuum solution, as a solution to your classical equations of motion, if your transformation is just pure gauge, at every equations of motion are local objects. They're solved point by point. A pure gauge transformation will solve it. However, these are topologically inequivalent gauge fields. Therefore, they will contribute to the path integral as different saddle points. Each of these guys is to be interpreted as different vacuum. Is that clear? Because equations of motions are solved they're local, they're point by point, but this is locally trivial. These transformations are locally trivial, they're only globally non-trivial. That's why they're related to instantons. These topologically non-trivial gauge configurations in Euclidean space are related to they are instantons for gauge fields. I'll give a better description of it. Yeah, this example that I just worked out, the AN North Pole, Northern Hemisphere, Southern Hemisphere A to source the monopole, right? As a topologically non-trivial U1 bundle on S2, right? Why S2? Because you had the magnetic monopole and then we're looking at the Coulomb law. I don't know if you see that. This is S2, and at every point, there's U1. All right. Any questions? Yeah. So you ask your question again.
So like you specifically mentioned what's in the
Yes.
like,
What was the reason for that you're asking? All right. Where did I use the Euclidean signature? I emphasized that last lecture. In Euclidean signature, so I had two terms in my Lagrangian, Yang-Mills, which had two time derivatives. And then I had the theta term. In Lorentzian spacetime, all of this was I multiplied by this divided by h bar. The theta term has one derivative. In Euclidean space, the Yang-Mills term is just a measure, right? E2 minus something positive. But the theta term is a phase. That's original quantization. Quantization of the charge, right? This whole Dirac quantization has to do with the fact that it becomes a phase. Good. That's why, yeah. Any other questions? All right. So theta term in 4 dimensions. Consider Maxwell action in 4 dimensions. It's this and Einstein Maxwell. Oh, sorry, not Einstein. Maxwell. So electrodynamics. It's just E squared plus B squared, right? Charge and electric field and magnetic field. We defined a dual tensor, and then you said that the dual tensor is like F mu nu, but the difference is that E goes to B and B goes to minus E. You can put in the factors of 1 over the speed of light in there, as you wish. All right, so S theta is the theta term. It's theta over E squared over phi squared. The dual F mu nu Lorentz contracted with F mu nu. That corresponds to, in the abelian theory, is E dot B. That's what the term is. In 4 dimensions, theta is dimensionless, so it's a theta parameter. And S of theta is a total derivative. So you can write this down as del mu of this term. That's why we say it's topological. It does not change the equations of motion. It's a purely boundary term. For U1 abelian theory. It's important. With a very, very important for the abelian. I also commented very briefly on axions. Axions are the things what we call it. An axion is a setup where we promote the theta term to theta parameter to a field, dynamical field, and we will add a kinetic term for it. That's called axion electrodynamics. It will change the equations of motion because now the field can have a gradient, right? And we said that the gradient on this side acts like an effective charge density. And over here, it acts like an effective current density, right? We give an example of this in terms of topological insulators. We said topological insulators are type of material where they act like theta equal pi inside of material, and theta is equal 0 is outside. So because the boundary of a topological insulator gives you a jump from theta equal pi to theta equal 0, it will give you gradient of theta. It will actually induce charge and current density. We said that if you apply magnetic field outwards, perpendicular to the boundary, it will create electric field parallel to B. If you apply electric field parallel to the boundary, it will create magnetic field parallel to boundary outside. All right, those are topological insulators. Any questions? Why is theta periodic? So here's where I messed up last time. In classical E&M, theta can take any value. However, in quantum mechanics, it has to be periodic between 0 and 2 pi. That's why we call it a theta angle. And we'll see that the origin of that is the fact that S theta becomes H bar theta n an integer. Right? I put H bar here so that we divide by H bar. Right? It contributes to the partition function as e to the power of I n theta and what's that we thought? Non-natural numbers. Integers. The fourth theta is periodic. And as I said, the origin of this I is the fact that it has one derivative in Euclidean, right? So phases in partition functions are not cool. They're weird, right? Well, they're depends. Depends. But do think about it, what a phase is in partition. All right. Consider so now our goal is to show that to fix what I did last time and show that the theta action is basically theta multiplied by an integer. This integerness has to do with the fact that it's topology. It's actually counting fundamental groups, the Z. There's a fundamental group of these topological non-trivial configurations, and let's see. Yes, that is not clear to you guys, but doesn't matter.
And if it's like a different page theory, would it be of whatever?
So the gauge field is or gauge transformation is a map from R4, 4 dimensions, to G. Right? Now, actually R3, because you set one of them to 0. The A0 decouples. Right? A0 decouples, so R3. I'll say in a bit that this actually becomes S3. We would like the gauge transformations to be trivial out at infinity. That means that at infinity, you can view it as just a compactification of it, R3, so it becomes S3. Then it becomes pi 3 of G, which is Z for all Lie groups of interest.
Oh, so how can we not? Okay, cool.
Because of S3. Yeah, I see what you were. Yeah, I see what you're saying. Consider U1 gauge theory on T4. This is 4-dimensional torus. We're gonna have put constant electric and magnetic field in the Z direction. And I'm gonna separate the time always, right? That's why I'm talking about vector E and vector D. So S theta is a Euclidean space-time integral of E dot B, which I can view as E dx0 dx3 dx1 dx2 B. So each of them are like torus integrals of a constant. Good. Now, here's a principle. Imagine, so in all these cases, you have a compact direction S1. There's a reason I picked T4 because it's simple. Consider S1, you have a gauge field that lives on this S1. Take the zero mode of this gauge field. The zero mode of this gauge field has to be identified, has to be periodic with periodicity h bar over ER. R is the radius of the circle. The reason is that a large gauge transformation like this, right, transforms A1 this way. So that's what's desired, right? It transforms A1 this way. Magnetic field is just del 1 of A2 minus A2 of del 1. So we can set A1 equal to 0 as a gauge choice, and B could be del 1 of A2. Integrating this, B is constant, A2 is Bx1. A2 is not single valued, but periodic with periodicity h bar over ER. Putting these two together, you learn that B has to be h bar n over 2 pi ER squared. This is quantization of flux, right? The flux that goes through this quantized. The volume, the amount of flux is quantized in volume. This. Right? the amount of flux is quantized here. That's just an integer. Flux quantization. Similarly, the same holds for E. You put the B and E together, you do the integral, you find integral of E dot B over this as 4 pi squared H bar squared over E squared N is N prime, which is like an integers. Therefore, theta has to be an angle. All right, so with that, we now finally start talking about new stuff. Theta-Angle and quantization. I'll be very brief, actually. Any questions? So first thing is now I'm gonna start talking about the non-abelian gauge theory. Here's a Lagrangian. This is the Yang-Mills term. Here's the theta term. So one thing that's important is that every time I'm talking about these kind of gauge theories, there are two things I do. I sometimes talk about setting A not equal to 0, the 0 component of A equal to 0 as a gauge choice, and write everything in terms of three-dimensional things, right? Another thing that we could do, we often do, well, actually, yeah, no, let me not philosophize. What I was gonna say, let me just say it. By splitting space-time into time and three-dimensional space, what I'm doing is I'm going to the Hamiltonian formulation, right? Now my Hamiltonian, my charges are integrals over three-dimensional surface, right? This is when you take the 4 dimensions and write it as 3 times time. So you're actively integrating things over three-dimensional surface. Another thing that's common to do is to just integrate over the whole space-time, but keep a boundary. And that's a three-dimensional surface. Yeah. Right? So, yeah. But I'm doing the first one. So EI is just A dot I. I apologize. Let's see. Do I apologize? No, I do not apologize. So I here is the space-time space index, right? Because I put 0, and I'm suppressing this A index, the Lie algebra valuedness. Previously, I was always ready. I was trying to make sure every time I wrote these expressions, I would write A mu A, omega A, right? To make sure that it's clear that there are Lie algebra values for non-abelian gauge theory. Here, I'm just simplifying my notation. So that hence all these traces outside. So Lagrangian density is going to be E squared minus B squared, but I'm just going to write E squared as A dot squared. Plus theta over 4 pi trace of E dot B, because I'm non-abelian, right? A dot B. An important thing to remember is that in non-abelian gauge theory, F is not gauge invariant, right? F is not an observable. There's Gauss's law, which is di ei z0. This is a constraint on all physical states. Again, I is a space index, and these are Lie algebra valid equations. This can be viewed as an equation of motion for H0. Now, because I want to do a canonical quantization, I'm going to look at the conjugate momentum, right? The conjugate momentum is, I have to take my Lagrangian and take a derivative with respect to A dot. That gives me 1 over G squared E plus theta over 8 pi squared b. So first observation is that theta shifts the conjugate momentum. The Hamiltonian is still a trace of e squared plus b squared, right? But the Hamiltonian written in terms of momentum, b and its canonical conjugate now has this extra shift, right? So it's clear what's happening. The expression for the Hamiltonian is still a trace of e squared plus b squared, but b is no longer the conjugate, right? So there's this shift. So e is not no longer conjugate. So theta angle enters only the definition of the canonical conjugate, the Poisson bracket, Pascal Poisson bracket. But importantly, you still have this equation, di of pi I is equal to 0. Why? Because we have shifted, pi I is actually ei plus this theta dependent term. This vanishes by the Coulomb law. This vanishes by Bianchi identity. So really, not much changes, except for the definition of pi. This should be familiar from your advanced quantum mechanics. I don't know if you guys see this stuff in advanced quantum mechanics. When you solve hydrogen atom or some sort of any quantum mechanical problem with some sort of background gauge field, background gauge potential, background electric field, this comes up. This canonical conjugate is shifted. In quantum mechanics, we need to solve the Schrodinger equation. The Schrodinger equation says the Hamiltonian acting on psi is E psi. Hamiltonian here is G squared trace of minus I del A, right? Yeah, no, summation over indices is implied. Del A minus theta over 8 pi squared b squared plus this. This is the Hamiltonian. Combined with the constraint that was this. Now, here's what happens. Consider a solution with theta equals 0. So psi naught solves the Schrodinger equation for theta equals 0. The claim is, if you define psi theta of A as e to the power of I theta, W of A, that I'm going to define for a second, it will solve this equation of motion for non-zero. So the wave function that solves the theory, the equations of motion with, sorry, I say equations of motion, solves the Schrodinger equation with theta non-zero is a phase multiply the ones with theta equals 0. Now, what is that phase? This is a functional of A. What is that functional? This is the Chern-Simons function. You could explicitly check that e to the power of I, this guy, theta, psi naught, you plug it inside this equation, you see that it solves this equation. If psi 0 solves the theta equals 0. Theta is in here, right? It's in the Hamiltonian. Any questions? Di pi r, yeah. Yes. Yeah, okay, very good, very good. We're solving, very good, thanks for the comment. We're solving the equations, so the wave function, because as we said, the theory is non-local, right? So even though A is, there's gauge independent, there's gauge redundancies, your wave function of null is going to depend on this guy because of these non-trivial topological gauge configuration that we're gonna consider to be physical. So it's going to be a function of this piece, right? The canonical conjugate to that is this thing, right? Now, B was I think I misspoke. That's what happened. I'll apologize for that. B was the curl of this A, right? And then E is E, right? E is defined as in terms of F, and F is defined in terms of A. Right? So I think where I misspoke was that I was trying to, I said the canonical conjugate to B. So that we're solving the equation. Here, B and E are just short form for these F and epsilon tensors multiplied, right? These are all, you're solving the Schrodinger equation for A. Everything is a function of A. Sorry about that. Here's precisely the point. When you vary W with respect to AI, you're going to get BI. So as a matter of fact, if you take psi theta and vary with respect to AI, you're going to get this expression. And it's straightforward to check that psi theta of A satisfies the constraint. So it solves the Schrodinger equation, it satisfies the constraint. It's the physical wave function. So the physical wave function ended up with some sort of theta. Chern-Simons functional is not gauge invariant. It's not gauge invariant, but it depends on the gauge in a very non-trivial way. Only it basically captures only the topologically non-trivial gauge transformation. And it actually calculates for you the integer, which tells you the number of times you wind around. So that we have to show. It's just n. For a topologically non-trivial gauge configuration, when you evaluate the Chern-Simons action, pure gauge, right? You evaluate the Chern-Simons action, you're just going to come out with n. Said differently, under a topologically non-trivial gauge transformation, Chern-Simons action shifts by n. So psi theta is also multiplied by this guy. So now, yeah. If you satisfy what? Yeah. Yes. Why? Because we wrote pi I in terms of EI and theta BI, right? The DI of BI was 0, but beyond that. Therefore, yes. Yeah, a lot happened. I went through that fast. Any other questions? So next, the point I'll try to make is to convince you guys that if you evaluate W, Chern-Simons functional, on a pure gauge transformation, it will calculate for you n. So will I actually do that, or I'll probably start the argument and then you'll have to finish the calculation yourself. Good. So consider R3, because everything is a function of this three-dimensional thing now. Under gauge transformation, non-abelian gauge field transforms this way. This is the Lie group valued gauge transformation. This is the exponentiated version of the Lie algebra gauge transformation. Now the Chern-Simons action, you could calculate directly. It shifts under this gauge transformation by a total derivative plus an extra term. Now, what is important to notice is that when so this Chern-Simons action, actually, I think, let me show it to you. Where was it? Yeah, here. So when the theory is a billion, this is the only term that there is. This term is not there. Right? Now, I ended up with two terms. One of them was this, which ended up being a boundary term, and this is the term that doesn't matter. So here is a place, this n I'm talking about, it's related to, it's relevant for non-abelian gauge. So this is the standard boundary term, total derivative term that we're going to get rid of the usual way. Now I have this extra term that has to do with the non-abelian gauge transformation. Now we're gonna set the gauge transformation to be 1 out of infinity. Right? We don't want anything non-trivial happening at infinity. When we do that, we can basically think of omega as a map from, instead of R3 to G, to a map from S3 to G, because you're adding a point at infinity to R3. That makes it S3. All right. So if you know some homotopy theory, this integral for a gauge transformation like this evaluates to n. N is the winding number, and it's just the winding number that labels this homotopy class pi 3 of G. Why pi 3? Because we're in 4 dimensions. If we're in lower dimensions, what other dimension would matter here? So the theta term, you could add it in to the even dimension, right? So in 2 dimensions, you could add it. Then it would be 1 dimensional. So you're going to be dealing with pi 1. So, for example, one example to keep in mind is example of the gauge group being SU2. A gauge transformation that's topologically non-trivial here is e to the power of I omega r sigma dot x. This sigma are basically the generators of SU2. Right? So it's Lie algebra valued gauge field. Good. We're going to pick omega of r to be 4 pi n at infinity and 0 at 0. So as you go from point 0 to infinity, this gauge transformation n times becomes 1. Anyway, I know that this was a really fast discussion, but the thing I want you guys to think about, have in mind, is again, what we're dealing with are these topologically non-trivial gauge configurations, right? Topologically non-trivial gauge configurations, they're pure gauge. So locally, the equations of motion are the same, right? Locally, you don't see any F mu. It's some topological obstruction, right? And we said that's actually the core idea behind gauge theory. The core idea behind gauge theory was that we couldn't describe the theory using F mu nu in a local way, right? We needed a mu nu because of this topological non-locality. Now, I think when I said this topological in a couple of like QFT1, I didn't quite explain why I'm calling it topological. Hopefully now it's clear. Yeah. Yeah.
And then that we have to do with the and how is that like I don't think it's like this goes to like
I'll explain that effect. Yeah. I mean, yeah. So the multi-valuedness of omega gauge transformation has to do with instantons. I explained that these guys give you solutions to equations of motion, right? So, sorry, what was your question? Oh, theta. So the connection between these, how the existence of theta term could be used to think about instantons. How is the instantons and theta term related? Right? I'll say that. Right? That's exactly my next. It's a trick. It's a very, very simple trick. So for one thing, it's the coefficient of the theta term which captures the winding number of these topological non-trivial. So in the action, you have two terms. There's a Yang-Mills term, which is a local interval. It's local. There is a second term, which is total derivative, right? Or this theta term. That captures only topological non-triviality. So that theta term responds to this topologically non-trivial operator. Right? Now, when you have theta equals 0, all these different instantons contribute to the partition function equally. Right? They contribute equally. But when theta is non-zero, the contributions to the partition function differ. So they have to be added up. There's the issue of they appear as phases. So you have to make sure that everything is well defined, the partition function makes sense. You end up with quantization principle for your, well, theta, the range of theta becomes periodic, becomes an angle. Right? So one way of saying all of this is that there were two terms in the action. There was one topological, one local term. The topological term basically only responds to these topological non-trivial gations. It doesn't see local physics at all. Whereas the other term only sees local. So there's a separation of. So when you want to compare the role of these two guys, you need to turn on theta. I'm going to explain this a little bit more in a second. So let's forget about this. All right. So this is, I think, the last point of the one. Question?
That is true even for manifolds with boundary.
Yeah. But manifolds with boundary, you have to treat the boundary carefully. Because we said that in the presence of a boundary, Chern-Simons term is not being there. Right? So yeah, that was the anomaly thing. So anomaly has to be cancelled somehow. Right? Let's assume there's no boundary. It goes all the way to infinity and omega goes to 1. So the only topological non-trivial thing have to do with, for example, some sort of topological non-trivial thing on a sphere that surrounds the monopole or things like that. Let's not deal with infinity for now. That's a whole extra story. Yeah. In which discussion? Yeah. The moment you make this a dynamical field, well, yeah, when you make it dynamical field, it's no longer, well, actually don't know. It's very well studied. I'm tempted to say that, let me think for a second. Yeah, I'm tempted to say that the whole topological thing goes away. Right? Because when you vary your field, right? So now theta of x, t sits inside the integrand of space-time integral next to some other thing. It was for Chern-Simons term to be, or for the theta term to be topological, it was important that these terms were adding up nicely, right? There was no, yeah. Another way of saying all of this, well, do I want to say that? Yeah, let me know. Okay. No. There's local physics that changes, as we saw in the case of topological incident.
What do you know about this? Yeah, I mean, the application there.
Sorry, I have a little bit of a problem. Yeah, let's discuss this later, but I don't think we. The reason is this, what is the term you want to write down? So you have the integral of trace of star f mu f mu. This is a function of a point space time, and you want to put phi of x in t and integrate over our point. Right? It's this thing, the zero mode of phi xt, which is topological. Right? It's a zero mode of it that's topological. So there's topology plays a role, but that's more complicated. As a matter of fact, this term appears on the right-hand side of the equations of motion for phi. Right? This is f wedge f. It's like anomaly term. It's exactly the same anomaly term that appears over there. Right? It's complicated. Let's just say that I'm ignorant about stuff I don't know them well. But it's Q52 towards the end of the semester. You guys can learn and teach it. Right? So, all right, now here I want to give a little bit of a trick to make sense of instanton and to comment on relation between instantons and trivial topological and non-trivial field configuration. Okay, imagine you have one of these topological and non-trivial field configuration with integer n or nu. I think I'll call it nu. Of course, it solves the classical equations of motion. So that every point f mu nu, like the local physics, gauge invariant physics, is going to be invariant, right? Here's a trick we're going to play. We're going to write down the Yang-Mills term as in the following form. We're going to write f mu nu minus plus star f mu nu squared minus this term. Right? So this is the standard theta term. This is the thing that has the combination of the two, and this is the Yang-Mills. Now, this is larger than this term. Why? But the first term is positive. Right? So it's a positive number plus the theta term. Let me call this n. N. Good. Now, when we're trying, this is a trick. When we're trying to find the classical equations of motion, what should we do? We're trying to minimize S Yang-Mills. What is the minimum of S Yang-Mills? The inequality tells you that it could be arranged for if there are solutions to self-dual, anti-self-dual field spin. It's a trick, right? It's a solution generating trick. Now, it goes the other way around. If there are self-dual or anti-self-dual field configurations, they are minima, saddle points. But it's not like every saddle point. So they are special. So here's what I'm trying to say again. These are special solutions to the classical equations. Select solutions to classical equations of motion in the case of gauge theory. And of course, you do know what's special about it, right? They are topologically non-trivial and locally boring. As a matter of fact, locally boring or not, any local solution, any locally non-trivial solution could be added to these terms. So equations of motion are linear, right? So you could think of every topological non-trivial field configuration, gauge configuration, defines for you a vacuum, and all the excitations live on top of this vacuum. So your Hilbert space splits into many, many sectors. Each sector is labeled by one of these vacuums. Good. So solutions to the self-duality equation gives you solutions to equations of motion. Why? Because d mu of star f mu nu is always equal to 0 by Bianchi identity. So it's a very, very cool trick. These solutions are called instantons, and their action is this. This is the value of the action. Well, you're just adding and subtracting. Yeah, so they're talking about 3 plus minus. Yes. Yes. In the case of abelian, yeah, correct. Thanks for the question. Non-abelian, the equations are non-linear, so it's complicated. Linearity is important. Now, why is this a powerful method? You know why? Why is searching for solutions to trying to solve the self-duality or anti-self-duality equation is significantly easier than solving the equations of motion? Of course, it's not equivalent to it. It only captures the classical. How many derivatives are there? And this is the first derivative equation. Correct. Solving first derivative equation is significant. Secondary. This is an incredibly valuable trick. In the context of gauge theory, yes. Correct. Actually, that's my next point. In quantum field theory, an instanton is a topologically non-trivial field configuration that solves the classical equations of motion in Euclidean spacetime. Let me not comment on this. Sorry. However, in the context of gauge theory, we're talking about gauge transformations of the topology, right? Because the rest is like gauge redundancy. So let me wrap up the discussion this way. We're discussing special topics in gauge theory. Recall the origin, the basic idea of gauge theory that we discussed in classical field theory in field 1. The idea was that we wanted a local theory. We had a theory that showed non-locality. The physical degrees of freedom were B and E, but besides B and E, there seemed to be other observables to the theory that were non-local. And to make sure we could represent those degrees of freedom, as well, we introduced this redundant local description called gauge theory. Now, gauge transformations were unphysical, except for these topologically non-trivial gauge configurations, right? That point by point, they solve the equations of motion point by point. They look like the actual vacuum, but they're globally different, right? So this is an essential feature of gauge theory. It's not true that gauge theory is just electric and magnetic field. Gauge theory also includes these topological non-trivial sets. And the principal bundle formulation of gauge theory, right? Really, this geometric formulation of gauge theory really makes this click, the connection to topology. That's why the connection to topology is picked up so well. And topology is precisely why these integers are coming out. When you evaluate these are topological things, right? They're calculating some sort of a fundamental group thing or like pi 3 or right. So that these numbers that come out, they're discrete values. They have to do with groups, right? And they appear in the Euclidean partition function as a phase. So the consistency of everything leads to this theta parameter that we put in the action to be between 0 and 2 pi, and then there was some sort of gauge Dirac quantization, right? So that's the summary of the whole thing. This is fully non-perturbative. Why? Why is this fully non-perturbative? What is perturbation? You take equations of motion, you take a small parameter, coupling, and expand, right? Equations of motion are the same. These are topologically non-trivial computation. Locally, there's nothing to expand. When we were discussing standard model particle physics, I said, let's add a term for every single one of these guys, right? And then I said, oh, don't worry about them. Physically, they don't change anything. Why? Because we were doing Feynman diagrams. So at the level of Feynman diagrams, they don't change anything, but they change the spectrum of the theory. They really change we didn't get into it. The best discussion of this, I also recommend the discussion of QED, non-trivial gauge theory in 2 dimensions by David Tong. I prepared a lecture, but we're not gonna have time to discuss it. Over there, 2D gauge theory is so simple. You see actually how the spectrum of the theory changes. The story of instantons is complex. They have to do with phase transitions and bounces. There's like a lot of literature out there, but the goal of this second part of QFT2 is to give you guys a glimpse of what kind of non-perturbative tools are there out there so that you go and learn about them. Quantum field theory is not just perturbation, as you follow it out. And the fact that things are non-perturbative doesn't mean that we can't see anything. Topology is one of those special cases in the gauge series where you can actually make crucial statements. Now, one thing to remember, what is a saddle point approximation? So take your path interval. Or actually, you have 5 into minus S5 over H bar. When H bar is small, we do a saddle point approximation. Now, what if there are a couple of saddles? How does saddle point approximation change? Well, you will have to compare the value of the saddles, right? The dominant saddle, right? So let's pick the regular dominant saddles, for example, phi equals 0 in the simple case. And then what's going to happen is that you're going to have a perturbative expansion H bar next to the classical thing. So there is a classical action, H bar squared. These are perturbative. H bar is small, and these are power series in H bar. Now, when you have an instanton that has unshelled action different from the actual, like two instantons that have differential action. The contribute to the path integral, the contribution to the path integral is different by an exponential of 1 over h bar. So one of them, the dominant saddle wins exponentially. So non-perturbative corrections are exponential. These are exponentially suppressed. Now, h bar in gauge theories is 1 over g squared. Right? So we're talking about G squared. G squared. So you'll have a perturbative expansion this way, G squared, blah, blah, blah. And non-perturbative effects of the type instantons are e to minus 1 over G squared, blah, 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 these orders. So keep this in mind. These kind of structures appear in saddle point approximations all the time, right? These are non-perturbative, precisely for that. Is it clear that this is non-perturbative? If you take this function, as g goes to 0, what is this function? It goes to 0, right? Can you expand this for small g? It has no Taylor span. Not perturbative. So, yes,
That is really of the same order as the product.
depends. Depends on, no, depends. It might not. Might not. So we're talking about, see, action is not the equation of motion. Oh, yes. Yes, but sits inside the path integral, e to power minus s of that, so they're different. Notice that in perturbation theory, when we did Feynman diagram, we took this guy, expanded it, so this is inside down here.